Okay, welcome back, everybody. It's 2:30, so we're going to go ahead and get started with the lecture today. Before we really start with the lecture, I'm wondering if there are any open questions out there about the semester, about how it's been going and so on. Okay, hearing none, we'll go ahead and get started with the lecture then. So today's lecture, we've spent a fair amount of time now looking at stress. We talked about stress as being a tensor quantity that has multiple components. Of course, we learned that a tensor was a more general version of a vector. So a vector is actually a tensor instead of just being a quantity on its own. What does that mean? So for what we're looking at in this class, a vector has one direction associated with it. It can have components. So in a three-dimensional space, it'll have three components, one direction. Stress as a tensor has two directions associated with it. And so, for example, you remember sigma xx, the subscripts xx means on the x face in the x direction. When we had xy, it was sigma x on the x face in the y direction. And so we began to recognize this idea of having multiple directions associated with a tensor. And then we began to examine how that has implications for the tensor itself. And one of the most important implications was that we could compute the principal stresses of that tensor. And so we did that with a couple of examples. Today we're going to look at the stress equilibrium equations. And really what we're looking at in this context now is how stress evolves spatially as load is passed through a structure. We need to understand that. We need to be able to predict it. We're going to eventually recognize that it's a set of coupled differential equations, which in fact are quite difficult to solve much of the time. And that's ultimately going to lead us into the middle portion of the course, where we look at approximate solutions to these difficult calculations so that we can simplify the solving of those differential equations. But before we get to that point, we need to, first of all, just develop those differential equations. So that's the goal of today. Now, in order to losing a little bit off the bottom of the slide here. Every time I go from computer to computer, I seem to lose a little bit. Can you guys see my screen? I feel like you're not seeing my screen at this point. Okay, so you're able to see the slides. Is the whole slide on the screen?
I can't see any slides.
I don't know what's going on. Let me see if I can reset that. Is that better? Can you see that?
Yes.
Okay, I don't know what's going on here, but seems like every day is a little different. Sorry about that. Okay, so in order to go through and compute these differential equations, we need to look at what we would call a parallelepiped. So that's shown here on the screen. What I've done is I've taken that stress potato that we talked about, that structure, that body through which load is flowing. Forces are flowing through it internally. And you recall we had taken a series of differential cuts. So ultimately we had a differential parallelepiped, which had, this is an infinitesimal volume of width dx, of height dy, and of depth dz. And here what I'm showing you now is a two-dimensional version of that. So here's dx, here's dy. The overall area of this particular two-dimensional differential element is now dx dy. And we're examining all the stress components that are present on that differential element. And in order to do this, to ultimately get equilibrium, we need to apply equilibrium. Of course, you guys recall that equilibrium is simply an expression of the sum of the forces being equal to the mass times the acceleration of the element. So I've written that. In this case, I've written it only in the context of the direction x. And so what I want to do now is identify all the forces that have components in the direction x. I'm going to go back to this slide for a minute, and I'm going to pause, and I'm going to ask for somebody, anybody, give me a set of forces in the direction x based on the stresses that are present here. I'll give you a little hint. Okay, we can start with the easiest one. That's this one right here. So while you're thinking, sigma xx is a stress that has units of force per unit area. Now we're trying to convert that into a force to put into our equations.
Take the stress times it by the differential area.
Great. So what's my differential area?
Delta y.
Okay,
Times
delta
x.
Well, which is it, delta x or delta y?
Delta y.
Yeah. So we have to be a little bit careful. We've got, implicitly, we've got a delta z too, although in this two-dimensional world, we're going to assume that that is a unit width in that depth direction. So therefore, the sum of the forces from this component here, sigma xx, is going to be sigma x at position x plus dx. Now note, I've got x on the left-hand side here. I've got x plus dx is on the right-hand side here. And so you can see I've got this entire expression, sigma xx, at the position x plus dx, comma y. That times delta y is a component of force in the x direction. Okay, without belaboring the point too much, we can now look over to the other side. Here we have the expression sigma xx at the position x and y. We can multiply that also by the differential length dy. So that's why I have these brackets here. So this entire expression is multiplying dy. And of course, that one now is in the minus x direction. So we're going to have a minus sign in front of that expression. Now so that covers this stress here and this stress here. Is that the only stress that has a component in the x direction? Well, of course not. Right? So if we look at some of these other stresses that we've drawn on here, we can look at sigma yy. We identify that that's in the y direction, so that one we're going to ignore. That's going to be on both the top face and the bottom face. We can look on this positive x face, and I can see tau xy, so this is the shear stress on the x face in the y direction. That's in the y direction, so we can ignore that one, and we can ignore the one that corresponds on the opposite side. And then the last two that I show here are the shear stress on the y face in the x direction. So tau yx, that's going to show up here. I'm going to do the top one first. Tau yx at the position x, y plus dy. That is going to be, again, this is a positive phase, positive direction assumption for a positive stress. So since that one's in the positive x direction, I'm going to add it. So plus dx, tau yx, x, y plus dy. And then, of course, we can look at the other side here. This is the negative y face. It has a negative direction stress. So negative negative is a positive stress. So tau yx, that's a positive stress, but this one happens to be pointing now in the negative direction in terms of the resultant force. So tau yx at xy, and of course that also multiplies the differential length dx. So here we have dx, that distance times that length times the unit depth. Now there's one more piece of the puzzle here that we haven't covered yet, and that's what I'm showing in the middle of this differential element. I've drawn a vector. It's probably tough to see, so let me go back to this slide here for a moment. So this arrow is in the positive x and positive y directions. I'm calling it B. This is what I'm going to refer to as a body force vector, or a differential force vector associated with this element. And it's associated in this context with the area in 2 dimensions or the volume in 3 dimensions. So this is the x component of that B vector times dx dy, so times the area in 3 dimensions, it would be times the volume. That is going to be a body force that's in the positive x direction. You can think of this term as being gravity. So that's gravity, or that's a centripetal force or a magnetic force or something that's acting on the body as opposed to on the surfaces of the body. Okay, so are those all the stresses? Yeah, so we've ticked off this one and that one, this one and that one, and then the other ones just have components in y. We got the body force, and the last piece of the puzzle is, of course, mass times acceleration, max. So mass times acceleration is just differential mass, that is density, times area dx dy in 2 dimensions, volume dx dy dz in 3 dimensions, times the acceleration in the ax direction. Now, lastly, we're going to manipulate that set of equations. Why are we manipulating it? Well, first of all, because we don't like this dx dy hanging out on the right-hand side. The differential volume becomes a little bit confusing in that context. Maybe that's not the right word, confusing. Maybe it's pretty clear what it is, but it doesn't benefit us very much on the right-hand side. So if we divide the entire expression by dx dy, so for the component sigma xx minus sigma xx, that's the numerator here, we're canceling the dy, and we have what's left is dx. So sigma xx minus, so that's sigma xx at x plus dx minus sigma xx at x, all of that over dx. That's this top term here. So we can kind of nail this term out of the way here. The next one is the shear expression. Now in this case, we're canceling dx with dx, so we get tau at yx, x y plus dy minus tau yx xy over dy. Of course, the differential area cancels in front of the body force vector, so bx just hangs out by itself, and the right-hand side now becomes rho ax. Now, this expression should be relatively familiar to you. I'm going to highlight just one of them, sigma xx at x plus dx minus sigma xx at x divided by dx. What's this here? Somebody throw it out.
It's a limit.
Well, it could be a limit. We can take the limit as differential x, dx goes to 0, and then what happens?
It's a derivative.
It's a derivative. Thank you. Thank you, Ethan. Thank you. Whoever said that, I'm not sure who said it. Great. Wonderful. So this one here is now a derivative, d sigma xx dx. This one here is also a derivative, d sigma yx dy. Note also, I'm using tau here and saying sigma. Tau and sigma are the same. Because this is a two-dimensional world, I left it as tau, which is sort of the convention in a two-dimensional world. But in my mind, it's always sigma. Tau and sigma both are shear stresses if they have the subscript yx or xy. So if the subscripts are not the same, they're always shears. And we don't need to worry about whether we're calling it tau or sigma. So that whole thing just simplifies to this expression. Partial sigma xx partial x plus partial sigma yx partial y plus bx is equal to rho ax. This is a differential equation. It actually has a coupling between the x direction, the y direction, the normal stress, and the shear stress. And then, of course, we have still this body force and acceleration term. Now, the body force and acceleration term, it's worth noting, I mentioned that you could think of bx as being gravity. Okay, so gravity, the force, the acceleration due to gravity is an acceleration, right? So it's rho ax. It has the same units as rho ax in this context. Okay, so we could have done an identical summation except summing the forces in y. Not difficult. You guys could do it in your sleep after having seen it done once. And what we get as a result is d sigma yy dy plus d tau yx dx plus by, this is now the component of the body force in the y direction, is equal to rho times the component of the acceleration in the y direction.
In the previous slide, it's shown as tau xy. Is that a mistake then for the equation, or? Yeah, so if it's going up and down, it's tau xy.
Yeah, great question, Scott. Let me go back to this slide here for a minute. Okay, so now if we're thinking about the components that have a y component, a force, so it's on the x face in the y direction, so we get xy. When we're thinking about the components in the x direction, it's on the y face in the x direction. And so these equations actually differentiate yx from xy. Now, here it looks like this one might actually be a typo. That one should be xy.
Okay, yeah, that's what I was asking about. Thank you.
Oh, thanks for pointing that out. I'm going to have to correct that in my web version of the notes. So excellent. So there we go. Now we have, what we have is we've got this equation here, the bottom one, and we've got this equation here. These are two equations for how stress evolves spatially. These are spatial derivatives with respect to the x and y coordinate systems in a two-dimensional world. Now, in a three-dimensional world, of course, we can do the same type of calculation, slightly more terms, not complicated. This now expresses all three directions. Sum of the forces in all three directions is equal to the masses times the accelerations. I'm also introducing, it's worth noting, a new notational scheme that I want you to get used to. This is a kind of a clumsy longhand version of writing derivatives, partial derivatives. So what I'm expressing now here, sigma xx comma x represents d sigma xx dx. I should say partial sigma xx partial x. And similarly, yx comma y, zx comma z. If you have this comma as followed by another subscript, that is now expressing a partial derivative with respect to that direction. Okay, so here we have it. We have three equations. These are derived directly from the sum of the forces in three directions. They do have all 9 components of stress within them. They are coupled differential equations that describe mathematically how stress, really load, how force, this is the intensity of force at a point in the body, how that is passing through the body and evolving spatially. It's worth noting that the form of these equations depend on the coordinate system used. What I mean by that is if you're using a Cartesian system, that's how I have expressed these equations. In a Cartesian system, that's an x, y, z, right? You know, orthogonal linear system. But we would have different expressions if we're talking about cylindrical or spherical or some other general curvilinear system. Okay, I will pause for a moment and take any questions that you might have. Now, if you're one to start preparing for the exam early, I would say that this set of equations that are on the screen now, this is an extremely important set of equations. You might want to have on a formula sheet or some sort of succinct summary of the course materials for the exam.
So are we going to be provided, or are we going to be allowed to have an equation sheet then for an exam?
Yeah, that's an open question. I think the answer is you will at least have a formula sheet, but I haven't entirely figured out how to do these online exams yet. We're gonna figure that out as we get a little closer. I'll certainly let you know when we get there. Okay, so I think that was a relatively easy calculation. It's simply algebra and then taking a limit and understanding what a derivative is. You guys have been doing that for years. I'm going to now take a look at, instead of linear equilibrium, that is translational equilibrium, I'm going to instead look at rotational equilibrium, what we'll call moment equilibrium. This is known as conservation of angular momentum. What we previously expressed was conservation of linear momentum. Here we're going to look at the same two-dimensional body. Okay, it's a differential, infinitesimal differential element called a parallelepiped. It's got those same stresses that we had previously. Now, instead, what we're doing is looking at the moment equilibrium associated with it. So moment equilibrium is expressed this way. It's a very similar expression to force equilibrium. So the sum of the moments is equal to some inertial term. Previously it was mass. Now I'm calling this the mass moment of inertia, times the second derivative of theta. That's a rotational acceleration. Now this moment equation has some subscripts associated with it. Because we're doing a two-dimensional calculation here, where x and y is the plane of interest, we're doing a moment sum about the z-axis, so the second subscript here is z. And I'm saying I'm going to take my moments about the center C of this differential element. As you guys recognize, of course, you need to have a reference point when you're calculating moments. Lastly, I'll say that for our purpose, we don't really need to worry about the inertial terms here. Why do I say that? If you think about this, we just went through and we did the limit as this becomes infinitesimally small. It's very difficult to imagine in the limit a rotational acceleration. It's not impossible. Physicists probably do it all the time. We as engineers can largely neglect it for our purpose and not have caused ourselves any problems. I guess the think about what a point moment would be. A moment without a moment arm. That's something we as engineers think of as being zero. So as in the limit, the right-hand side goes to zero essentially. So we're just going to ignore it for the time being. We're going to do the same type of calculation that we did previously. Now I'll go back to this slide one more time. What we need to do now is calculate moments about the center. Let's look first at the normal stresses. Do the normal stresses contribute anything to a moment about the center? Tyler says no. Scott's shaking his head. And you guys are absolutely right. And why? Well, of course, because the normal stress goes through the center of this differential element, so it has zero moment arm, so it does not contribute to the moment. So that's true of sigma xx, both positive and negative. It's true of sigma yy, both positive and negative. So that leaves us just 4 components of stress in this two-dimensional world that we now need to pay attention to. Okay, so now the next thing I want to look at is what do these other components contribute? So somebody give me a force and a moment arm associated with tau xy.
So it would be tau xy times delta y. So that's your force, and your moment arm is going to be, in this case, 1/2 of delta x.
Excellent. So you got it absolutely correct. That is going to be, if we need to state our assumption of what positive moments are. So if we say positive are counterclockwise about the origin, we could say that that expression that you just provided gives a positive moment. So it goes counterclockwise. Let me actually draw that on here so everybody has that sort of in their notes. So that's positive. About the center, tau xy contributes a positive moment. Now somebody give me tau yx. Very similar.
That'll be negative tau yx times dx for the force, and then times 1/2 of dy for the moment arm.
Absolutely. So this one contributes positive tau xy, tau yx contributes negative. Each of them ultimately have 1/2 dx dy as their multiplier in the equation. You can imagine doing that equally here on the opposite side. xy contributes a positive moment, yx contributes a negative moment, and they have the same moment arm as we had previously expressed. So in the end, this is what we get. These are what you gave me, absolutely 100% spot on. So delta y, delta x over 2, tau xy at x plus dx plus tau xy at x, and then you subtract off delta x times delta y over 2, tau yx at xy plus dy plus tau yx at xy. And that, since we neglected inertia, we don't have to neglect inertia, but we're going to here, and we're going to say that this is equal to 0.
I have a question.
Sure.
Why do we have to multiply times partial y, the tau, in the first equation, and likewise in the second equation?
Yeah, so the other students suggested it. I forget who gave us that answer, but the force is a differential area. So in this case, tau xy times dy times the unit depth. Okay, we can't forget that unit depth. So dy times the unit depth is an area times a stress, that's a force. So the dy for the tau xy comes from the force component, and the moment arm gets a dx over 2. Now conversely, when we're looking at this one, the dx times the unit depth is the area, times that stress is the force, times now dy over 2 is the moment arm. So it works out that they are functionally the same, except, so here dx over 2, that's the moment arm. dy over 2 is the moment arm. dy and dx times 1, the unit depth, were differential areas. Okay, so what do we do next? Well, in this equation, we can kind of do the same thing. We don't really have need for these differential elements anymore. So dx dy over 2, we can divide all of those expressions by that quantity. And so this is now what we have. Tau xy, x plus dx plus tau xy at x minus tau xy at y plus dy plus tau yx at y. And lo and behold, since this needs to be equal to 0, we can take the minus, we'll move it over to the right-hand side. So the xy terms are on the left-hand side, the yx terms are on the right-hand side. Now, here, we need to think like we thought before, because this is a differential element. This applies, these calculations we're doing apply in the limit as dx and dy go to 0, as this infinitesimal element becomes infinitesimal. So what does that yield here? Let's look at the left-hand side. So in the limit, as dx goes to 0, the left-hand side becomes tau xy x plus 0 plus tau xy x. So that's just going to be equal to 2 tau xy. Similarly, the right-hand side in the limit becomes 2 tau yx. So ultimately, what have we learned from computing these the moment equilibrium on the differential element?
The tau xy and tau yx are the same.
They're the same. So recall at the end of last lecture, somebody asked me a question about why I used an xy in a location. There was what appeared to maybe have been a typo. Turns out it wasn't a typo. It's because tau xy and tau yx, we don't need to differentiate them. The stress tensor is symmetric. In 3 dimensions, this applies, actually gives us 3 equations. It's symmetric across the diagonal. So this term and this term are the same, this term and this term, and of course this term and this term are the same. So the unique components of the stress tensor are only 6. There are 9 components, but of the 9, only 6 are unique. So that's a pretty important conclusion, actually. All right, now let me go back here for a moment. This set of equations. I just want to think about these equations as a group. All right, we'll think about it in a 2-dimensional world. It's just easier. So I'm just going to cross this one out. And I'm going to cross this one out. And I'm going to cross this whole equation out. So just look at this 2-dimensional equation. Sigma xx comma x plus sigma yx comma y is equal to B, the body force, I'm sorry, plus the body force is equal to rho times AX. Now, let's imagine the scenario where we have something like a lap joint. That's this here. A lap joint. So this is like an airframe structure that's got a wing skin that the bottom kind of forest green, we'll say, is wing skin. This blue is maybe an adhesive that's bonding one wing skin to another, and then this, I don't know what kind of green that would be, tealish green, is another wing skin, and they're bonded together, and they're carrying tensile load. Okay, and we're carrying load through this structure. What does that set of equations mean to this structural scenario? Let me go back to the equations for a minute. Okay, I've crossed out the ones that aren't interesting. Now, or I should say they're interesting, but they're three-dimensional. We're thinking in a two-dimensional world now. Okay, so let's pretend that this aerostructure, this set of wing skins that I've referred to, is in static equilibrium. Okay, static equilibrium means it's not accelerating. It's just carrying the loads, but it's not, accelerating, moving, vibrating. So we can cross out A's because that's going to be equal to 0. Let's say the body forces are negligible, which in many circumstances they are. So gravity doesn't contribute substantially to stress. So what we have now is this set of equations. It's much more concise. Sigma xx comma x plus sigma yx comma y is equal to 0. Sigma xy comma x plus sigma yy comma y is equal to 0. Now, think about what this scenario presents us. What is sigma xx out here on the right-hand side, far right-hand side? I'm going to write an expression. I'll just say sigma xx. I'll say max, okay? Or applied maybe is better, but we'll use max since I already wrote it. Okay, so if I were to plot, I'm going to try my best to draw a horizontal line with my mouse. It can be a little difficult. Okay, now I'm going to draw a vertical line. And on the vertical axis, what we're plotting here is stress. Okay, so I'm going to say out here on the right-hand side, I've got a point where this level now is sigma xx. Okay, now imagine for a moment that this bottom green, forest green versus teal green, that they're the same thickness. Okay, what if they are the same thickness, what's the sigma value going to be over here? Sigma x on the left-hand side. Somebody give it to me. It's pretty easy.
Sigma xx max.
Yeah, right here. Okay, now, again, focusing on the forest green one here, the one on the bottom. What is sigma xx at this point right here where my mouse is?
Is it 0?
It sure is, yeah. Why? Because if we look at the traction vector here, we said tractions are boundary conditions. At this point, since there's no applied stress in the x direction and there's no applied stress in the y direction, there's no shear, there's no normal in a two-dimensional world, the traction vector here is 0 vector. So I'm going to plot here stress being equal to 0. Okay, I'm going to ask a similar question about this point, and the answer is, I think, relatively obvious. 0. Okay, now as we imagine sigma x as it varies in the green, forest green one on the bottom, from right to this point, now we don't have to be precise, we're just using intuition. Okay, we can do the real calculation and we can get an answer, but we're going to just intuit the answer. So do you think it's changed substantially by the time we get to this point here where my mouse currently is?
Wouldn't it stay at sigma xx max all the way until it hits the blue point?
Yeah, so
Right there.
it pretty much stays at sigma xx almost right to that point. Now, if we do a finite element analysis, it turns out we're going to get some really big stress concentrations in this area, but we're going to neglect that thinking for the time being. And we're just going to say that it basically stays the same till right about here. Okay, so that, again, I'm going to try and draw this horizontal. Those are supposed to be on the same level, okay? Then what happens between this point and this point? Well, it's going to drop, right? We don't know precisely how. I'll just draw it looking something like that. That's pretty realistic, actually. Now, same thing with, ask the same question of this other side. So that sigma xx is going to kind of do this. It's going to stay pretty steady. And then from there, it's going to drop, hopefully symmetrically, if it's made out of the same material. So pretend I've drawn this symmetrically, even though I did a poor job of doing that. See, I might even be able to, oh, no, that's not the right one. There is a key here where I can erase. I forget what the key is. We'll just ignore it. So it's symmetric, okay? Now, there we have sigma xx plotted from left to right. What we're seeing is that we're exchanging load. Load is being carried along the bottom. We're thinking of the load path, right? It's being carried along the bottom. As we get to this point, it's now being transmitted. It's moving through the structure, and it begins to be carried a little bit at the top. By the time we get to this point, it's picked up all of that load. And so what it's doing in the middle is it's decreasing on the bottom and increasing on the top. Now, how does it do that? To understand how it does that, we have to look back at our equations. So we said it was decreasing as we started at the right edge and moved to the left edge. So this d sigma xx dx is changing, right? Or it is a value. It is a derivative. So the stress derivative in the x direction actually, it is a changing value. So what does that mean? In order for this value to be non-zero, that means this value, sigma yx comma y, also has to be non-zero. So what are we learning? We're learning that because sigma xx changes, sigma yx changes. They are coupled together. You cannot have a changing sigma xx without having a changing sigma yx in the absence of a body force. Now, that's a caveat, and you'll probably encounter that at some point in the semester where I give you an assignment with the body force. But for now, neglect that. So shear and normal are coupled together. Okay, now the next thing we'll take a note of is that because yx and xy are the same, we know they're symmetric. We didn't need to differentiate yx from xy. Now what we're seeing is because sigma yx is changing spatially, sigma xy is changing spatially, since those are the same thing. And that leads us to have a non-zero sigma yy comma y. So what happens as sigma xx changes? Sigma yy changes. we're getting a normal stress in the y direction due to a shear stress on the x face in the y direction or the y face in the x direction that is due to a changing sigma xx. So how does that manifest itself over here? So what I plotted with sigma, I'm going to write that as sigma. I could have equivalently plotted tau. Now, what's the shear stress on the right-hand side? I think it's relatively obvious to everybody that that value is going to be 0. It's going to stay 0 as long as sigma xx doesn't change. Once we get to this point, what happens? Well, we get now a shear stress. We get a spike of shear stress that occurs. Okay, we'll deal with the spike in a minute. Let me ask you, what is shear stress in the midline of this thing? Okay, this is again an intuitive answer. The mathematics will confirm it for us when we did them. But because of the symmetry of this problem, we can intuit that the shear stress is symmetric about this point. So it has to be 0. And then, of course, the shear stress is going to pick up and be 0 again here. So we've identified a whole region of 0 shear stress. But at these edges where we get these larger changes in sigma xx, we're going to get spikes in sigma xy. And that one turns out to be anti-symmetric. So it looks sort of like that. And then similarly, we're going to end up having, I won't draw the spikes because they're similar to the shear looking spikes, but the sigma YY stress also spikes in those locations. So even with this really simplistic lap joint configuration, because of the equations of motion, because of stress equilibrium equations, we get this coupling between normal stress, shear stress, and normal stress that leads to these massive stress concentrations that occur. And this is the most likely failure location is right here and right here, where you're either going to get a peel failure at the interface between the adhesive and the wing skin, or you're going to get a shear failure at that location, because both the peel and the shear stress spike, and in fact the sigma YY spikes a lot, so you tend to get this peel failure right there. And then once it's failed there, then it propagates inwards and the whole thing fails. Okay, so I'm going to pause for a moment, let you guys digest that and ask any questions that you might have.
I have another question. Is the y direction, in this case the vertical axis, is that just the magnitude of sigma, or is that tau?
Well, so this y direction, I'll extend it all the way to the top. So this is a plot of sigma and tau. Okay, I should have multiple colors. I know I can do that. I don't know how to do that, unfortunately. So I should have drawn all the sigmas in one color and all the taus in another. But these two that I'm highlighting, those are the sigmas. This is the tau, anti-symmetric. And then the sigma YYs would spike sort of like this. Okay, so Nicole's asking a question in the chat. Can you explain again? Is this still a relevant question, Nicole? Can you explain again how you know where the stress is sigma max and where it is 0? So yes, so we know it's going to be sigma xx, the maximum load that this structure carries is going to be on the right-hand side and the left-hand side. That's where the load is applying, and it's where the material thickness, you can think of what is stress, right? It's an amount of force over an area. And so out here we have a very thin material that's carrying it. Out here we have a very thin material that's carrying it. In the middle, we have more material that's carrying it because the load is shared between the top and the bottom. So the stresses are going to be lower in here. So we know they're max on the right-hand side, max on the left-hand side, and it transitions through to 0 in the forest green on the bottom. It transitions through to 0 in the teal green on the top. And so that's these, I know it's hard for you, the mouse is not updating quite as fast on your screens as it updates on mine, but these stresses that I've plotted, that's what's going on there. Okay. I'm not seeing any more questions. So let me pause for just a moment here. Uh-oh. Baseball stats. Let's see here. Where is... Okay, we're going to go ahead and get started actually with what I'm calling Lecture 7. We were a little bit behind, and so, we kind of, a series of lectures took a little bit longer. Now we finished that series of lectures. Don't worry about the number so much as just the content. So we're going to start now the next lecture. I spelled displacement wrong. So here we have displacement and strain. So what we've talked about up to this point is exclusively stress. Okay, we have not talked about strain yet. Now you guys remember what strain is in simplistic terms. It's the change in length over length. We realized that stress was more complex than it had been presented to you previously. So I'm now going to argue that strain is also more complex than we had previously presented it to you. Now we're going to look at strain ultimately in 3 dimensions. That's important. We're going to quickly realize that strain is also a tensor. It's going to have 9 components. It's going to have 6 of them unique. We'll actually derive that again like we did for stress, although it's for a different reason. We need to recognize that strain is derivable, or it is derived directly from displacement. Okay, that's kind of like saying stress is derivable from force. Okay, strain is derivable from displacement. Strain really has, we have to be careful and say it's not related to stress, or at least it can be unrelated to stress. In most cases, in all materials, most materials, it is related to stress, but that's through a stress-strain relationship. Really, the definition of strain is a differential relationship with displacement that you will see shortly. Now, in your prior courses, you probably saw something like this. This is what I'm going to call the small deformation definition of strain. This is the linearized definition of strain. What we give you is this. Strain is defined as the limit, as the length goes to 0, of the change in length over the original length. Okay, and that's a good definition. In fact, it works for much, if not most, of our engineering mechanics. However, it in fact is what we will call a linear approximation. It actually isn't the best definition of strain, and we'll get into the more advanced definition of strain in this class. And then ultimately, we need to recognize that the larger the deformation, the worse this equation becomes. Okay, of course, this equation as written is one-dimensional. We recognize now that we have this concept of a tensor, and so it's not one-dimensional. It's going to have 9 components. Again, I will highlight that this makes this critical assumption of having small strain. For some material that we'll cover in this lecture, and particularly for aerospace structural mechanics in general, this linear approximation of strain is actually insufficient. There are many circumstances where we need to carry a better definition that has higher order terms in it. Circumstances like buckling calculations, stability calculations for structures all require the more advanced tensor definition of strain. So we'll get to that next. Now, I'm going to look at in the next few slides our definition of normal strain, and this is for larger deformations. Now, this isn't for the largest deformations, it's for larger. So not small deformations, larger deformations. As I mentioned, strain is derived from deformation, so we need to look at deformation. What's deformation? Well, deformation is we can take a point in a body. As it is loaded, it is stretched. It's strained, in fact. It changes. And so we can imagine a point in that body. That point we're going to call O. Okay, it's at an origin within that body. And it has we can imagine that there are actually 2 points, one of which is A, that is a differential length, a small distance from the origin. So we're going to call this a vector OA, and we're going to imagine how that vector stretches, how it changes as it deforms, as the whole body deforms. Now, for our purpose, we're going to assume that this vector OA is aligned with the x direction. And we're going to ultimately compute what we're going to call the normal strain. That's epsilon xx. Normal in the sense that we have normal and shear, just like we did with stress. And so xx, 2 identical subscripts, xx, yy, and zz are all the so-called normal strains. And then we'll have shear strains xy, xz, and yz. Okay, but we're going to focus first on the normal strain. Okay, so when I say this assumption is not necessary, that's the assumption of it being originally aligned with the x direction. We don't need to do that. However, it makes our calculations easier, and it's perfect for our purpose here. So we're watching this vector deform. Okay, as it deforms, so the original point O, the origin of our tracking, deforms. It moves from that position to a new point, what we're going to call O prime. Okay, here's O prime, and here's O. And we're going to have another point. That other point A is going to go from its original position A to a new position A prime. So as our body is moved, O and A have both moved. Each of them has moved by a vector displacement to new positions. Now, for our purpose, we're going to assume and then actually verify or compute that our higher order calculation of strain can be written like this. Okay, we're going to prove it in a minute, but we're going to assume that epsilon xx is going to be in the limit as OA, that's the length of this vector, goes to 0. So you can think of that as being the limit as dx goes to 0 of O prime A prime squared minus O prime, I'm sorry, minus OA squared. So these are lengths divided by 2OA squared. So this is, you can think of this as being a quadratic version of change of length over length. And you can simplify this expression to be the limit. We're going to carry the 1/2 outside as a constant. So O prime A prime squared over OA squared minus 1. Okay, it's noteworthy that we have a quadratic equation, so it's no longer linear with respect to the vector length. So this is a higher order approximation of what strain is. The previous version we gave you was linear. This is a second order version. All right, so now we got to get into the nitty gritty. Okay, if we actually write OA, the vector, and we write it out as vector expressions, we can see that the vector from here to here, O to A, is equal to dx, the length dx. It's a magnitude in the I direction, so it's aligned with the x direction. It has no component in j, it has no component in k. Okay, the new position, O prime, we're going to assume that we've moved a distance u in the x direction. So that's this one here. Note that's the one aligned with the x direction. It's going to move v in the y direction, so that's this one here, and it's going to move w in the z direction, and that's this one here. So here are our components of a vector that describe the motion from O to O prime. So that's ui plus vj plus wk. Now that in and of itself is not terribly difficult. Okay, that is, we're assuming that that's the deformation that occurred. Now the next thing we need to do is look at how A moves. So here we're staring at A, it's moving from A to A prime. How is it going to move? Well, what we're going to assume is that O and A, since they're part of a single body, they're going to move similarly. You know, if these 2 points are close to each other, they're going to move in a very similar manner, but that they're going to move slightly differently. Okay, so slightly differently means that A, as it moves from A to A prime, it moves that same u plus v plus w in the I, j, and k directions, but it's also going to move a small differential change in u, so u plus du. So it's u plus a little bit of a change in the I direction, plus v plus a little bit of a change in the v direction, plus w plus a little bit of change in the w direction. So they move similarly, but not the same. Now, momentarily set that aside and just think about the vectors themselves. So one of the things that we can try and write a vector describing is the relationship between O and A prime. Really, what we're trying to do here, I want to take you back, big picture stuff, is write these expressions. O prime, A prime, OA, OA. So we need to get to O prime, A prime. We need to get to a description of this length. And in order to do that, we need to sort of go through a series of changes. What can we do? Well, we can look at how we can look at O to O prime plus O prime to A prime. We can look at O to A plus A to A prime. these are two different paths that we can use to get from O to A prime. So if I write O to A prime, it will be O to A plus A to A prime, or it will equivalently be O to O prime plus O prime to A prime. Those are two equivalent expressions right here. And so the one that I'm trying to get at here is this one, O prime A prime. So I isolate that. So O prime A prime is now going to be equal to OA plus A prime minus OO prime. So this is nothing here. All of this stuff here is nothing more than vector summations describing these vectors. Okay, now again, we can look at, I've expressed each of those now in terms of dx, u, du, v, dv, and w, dw. So if I write now O prime A prime, it's going to be dx in the I direction plus u plus du in the I plus v plus dv in the j plus w plus dw in the k minus ui vj wk. And so O to A prime is now simply going to be equal to this expression here. It's the original length dx plus these small terms du in the I direction plus dv in the j direction plus dw in the k direction. So that's OA prime. We can then square that. Okay, so dx plus du squared plus dv squared plus dw squared gives us this expression dx squared plus 2 dx du plus du squared plus dv squared plus dw squared. And then we can divide that, of course, by OA, which was the original. And after expressing all of those things and simplifying, we end up with this expression on the right-hand side, 1 plus 2 du dx plus du dx squared plus dv dx squared plus dw dx squared. So just for clarity, this expression here, O prime A prime squared, really what we're doing is we're dotting O prime A prime with itself. So that's where the unit vectors go away and the remaining terms sum. Okay, questions? All right, so that expression, let me go back one more. So here we see on the right-hand side, we have this 1 that's hanging out. Okay, I don't necessarily like the 1 that's hanging out, so I'm going to subtract it from the right-hand side. I'm going to put it on the left-hand side, and then ultimately we have this 2 that we're going to deal with as well. So if I subtract first, so this is the dot product O prime A prime over the dot product OA, so that's length squared, you know, it's new length over old length minus 1 is equal to 2 du dx plus du dx squared plus dv dx squared plus dw dx squared. Now these terms on the right hand side you can think of as being in the limit as the length goes to 0, delta x. These are derivatives, du dx, dv dx, dw dx, partial derivatives. So epsilon xx, this is the expression that I previously wrote. It was the limit as OA, the length of that initial vector goes to 0 of 1/2 of this component, ends up being on the right-hand side. Now, so I canceled the 2 here by saying assume that this is defined as equal to 1/2 that. So what we get is epsilon xx is equal to du dx, the 2's gone away, plus 1/2 of this du dx squared plus dv dx squared plus dw dx squared. Now, this, the box that I'm drawing now, is the complete expression for our higher order tensor epsilon xx, strain, normal strain in the x direction. That's the complete expression. Now, you might say, well, how does that relate to the old expression that you told me when I was a sophomore or maybe a freshman? Well, it turns out that we didn't lie to you previously. We actually gave you the same expression. We just simplified it a little bit. Previously, we said it was du dx, change in length over length. Okay, change in length over length, du dx. We didn't give you these other terms, du dx squared plus dv dx squared plus dw dx squared. Why? Because in the limit of small strains, small deformations, when u and v and w are very small, these terms become small, du dx, dv dx, dw dx, and small terms squared become even smaller, and then of course multiplied by 1/2. So these are higher order terms. They go to 0 in the limit of small strain, small deformations. However, when we have larger deformations, we cannot neglect them. So we have to retain all of this for larger deformations. But for smaller deformations, like we gave you as freshmen or sophomores, this expression we previously gave you is perfectly adequate.
I have a question.
Yes.
Why do we switch from delta notation to the partial notation?
Because we took the limit, you know, you can express, so OA goes to 0. You remember the length of OA was dx. So in the limit of that going to 0, it becomes the definition of a derivative. And so I expressed it now as a partial derivative. Does that make sense?
Yes, thank you.
Okay, so we did that calculation with a vector originally aligned with the x direction. We could do an identical calculation or nearly identical calculation with a vector aligned with the y direction or one aligned with the z direction, and we'd end up with these results. Epsilon yy is dv dy plus 1/2 du dy squared plus dv dy squared plus dw dy squared. dz is similar. I'm sorry, epsilon zz is similar. And so in each case, of course, we have a linear term that's good for small strains, small deformations. We have higher order terms when we need to have higher order calculations. Okay, so we have now, with those prior slides, derived the normal strains associated with somewhat larger deformations. We have not yet derived the so-called shear strains. It's worth noting, though, that now we recognize, because we live in this three-dimensional world, that we have three normal strains. XX, YY, and ZZ, and we're going to see quickly that we're going to have 3 shear strains as well. Actually 9, but you'll see quickly that they're symmetric, much like we had with stress. All right, it's 3:44. We have just till 3:50. I'm wondering, it's probably a good idea to pause here, not start the next topic, which we won't finish today, which would be shear strain calculations. So we have a few minutes left for questions. I'll otherwise pause. I'm looking now at the chat list to see if I missed anything. I see Cole asked, Dr. G, can you hang out for a minute after everyone? Yes, I can hang out, absolutely. Nicole asks, can you explain again why the term with the 1/2 cancels out? So we're taking, so Nicole, we're taking this equation here, and I'm dividing that whole equation by 2. And that leads to this equation, which is what I am saying is our definition of strain. So it is by definition, epsilon xx is that expression, and its vector length, dot product of the old vector with the divided by the dot product, I'm sorry, dot product of the new vector divided by the dot product of the old vector minus 1, all of that divided by 2 is our definition of strain. It is what we're assuming strain to be. Now, we wouldn't have to have this 1/2 in front of there, and we'd end up with just carrying a new constant around. But this, the reason we do this is because this is what makes most sense with our prior understanding of small strain deformation. It's really easy to say strain is change in length over length, rather than saying, well, strain is 2 times change in length over length. So it's just the convention that we use.
So I guess my question is like the 1/2 term. So do you consider that when it's a large deformation, and then only when it only cancels out when it's a small one?
No, it actually is always present in our assumptions. Okay, this term here is the small strain definition. Okay, so it was always present, we just didn't pay attention to it. We never highlighted that for you. And the larger deformation version has this additional set of terms in it that wasn't present previously, or at least well, in fact, it was present previously, it just was negligibly small, because these small terms squared become negligible. So the fact that it was there, but we didn't pay attention to it.
But the one that you put the box around that formula, that's the large deformation one?
Well, no, they're both the large deformation one. This is our way of computing. So, no. The concise answer to your question is that this expression here is the large strain, or I should say moderately high deformations, large deformations, tensor definition of strain.
Okay.
That one is. Now, it was derived through this process, but that process assumed a convention which carries forward into this, but you don't need to worry about that convention exactly. It just is part of the convention.
Okay, thank you.
Yeah. Okay, any other questions? Okay, we're done for the day then. I appreciate your attention. Today being Tuesday, I will see you on Thursday. Catch me in office hours if you need me. I haven't had a lot of office hours customers yet from this class, but I hope to see some of you there in the next couple of days. Talk to you soon.